So today we're going to be talking about the combination of the last two. So we're going to have fundamental vibrations, which was 2 lectures ago, and we're going to have rotation, which was the last lecture. We're going to combine them, okay? The nice thing is they combine pretty easily because we just have rotational quantum numbers and vibrational quantum numbers. And so you can describe both transitions with their respective quantum numbers. So here we have our vibrational potential energy surface. That's the parabola, the harmonic oscillator that you guys learned in classical physics. And then on top of that, we have the rotational energy levels, which are really, really close together. Remember, pure rotation was in the microwave region, and vibration is in the infrared region. So the spacing between here is in the infrared. If I were to look at just the rotational, that'd be microwave spacing, really, really low energy. And yes, it's the same microwaves that you have in your house. Okay, so that's really kind of tuned to water and the rotation of water. And lots of things will absorb in that area. So the microwaves are tuned to heat up water. So if your food has water in it, then it's going to heat up. Okay, so that's pretty neat. But that's the microwave region. The infrared region is up here. And so we could have transitions that go from V equals 0 to V equals 1. That's the fundamental. And change the rotation at the same time. So that's rovibrational transitions. So we have a change in rotational quantum number and a change in vibrational quantum number. So we're going to zoom into this little orange area. Everybody see that? We're zooming in. Okay. And also from past experiments when all of spectroscopy was done with emission, the initial state was the upper state and the next state was the lower state. And so they did prime was up here and double prime was down here. Now, it'd be nice to flip that and just say we're doing absorption, but in your experiments, the lab handouts and things that you're going to read from your experiment from the published literature are using this scheme where the lower state is the double prime. So I have to introduce that here because that's what you're going to see in your labs. Okay. And then the single prime is the upper state. So this is the single beam infrared spectrum of air. So we have a hot ceramic source that's emitting infrared light, and we see the black body curve. So you see that shape that kind of looks like a black body, heat coming off of a black body. And that's what it is. So they call it a black body because it doesn't matter what the material is made out of. And that was another mystery of physics. It's like why doesn't it, aluminum and bronze and ceramic all give off the same infrared profile, and it's just a function of temperature, not what the material is made out of. So they said, the sort of what the material is made out of is just sort of a black box. We don't even need to know what it is. We just know the temperature and we know what kind of light comes off of it. So that's the black body, but then you see some missing light. You see all of these little transitions, these dips. That's where light's being absorbed by stuff in the atmosphere. So what do we have in the atmosphere? Well, we have water and we have CO2. So we have CO2 here and there, and then we have water. And it's in the infrared, so we know it's vibrations, but all these little sharp lines are also rotations. So we have rotations and vibrations happening at the same time. And then we have these smudges on my windows, which is bad. Somebody stuck a thumbprint on my window. Okay. So if we zoom in on this, we see these regular patterns. So this is what we're interested in right here. See those little wiggles? Every one of those little wiggles is a different jump from, say, a rotation level of 4 to 5 or 5 to 6 or 6 to 7. Kind of like our particle in a box when we had all those hot bands. These are the hot bands of rotation. And we have those at room temperature because the energy levels are so close together. So we have lots of hot bands in rotation. And we have R branch and P branch and Q branch, and I'm about to explain what those mean, okay? But we have all of these little rotational levels. So I put rotational transitions. That's what those little guys are. And then if we zoom over here to the parallel stretch, this is the one with the Q branch is a perpendicular band because the motion is perpendicular to the symmetry axis, and in the parallel band, the motion is parallel to the symmetry axis. And if it's parallel, it doesn't have a Q branch. We still have a P and an R branch. And so you see all of those little rotational levels. So these rotational transitions. So that's exciting, because right there, it's in the atmosphere. We have CO2. We just shoot infrared light, and we see all these little transitions. We have the center of this band, like right here, that's the fundamental. So V equals 0 to 1 for this whole thing. And then these might be like J equals like 7 to 8 or 8 to 9, etc. You know, just like we had the hot bands in the particle in a box. We have all of those in the rotational structures. Okay. So let's look at these Rovibrational transitions. So here we have that fundamental transition, the 0 to 1 transition for the vibrations. And we're going to plot that over here. Now, I've tried to fit everything onto one slide, but it's going to be difficult. So let me walk you through it. So we have the energy level diagram here, and this is the energy equation for the rotational levels at V equals 0. So that's down here, right? That's this first one right here. We have J equals 0, V equals 0. So every level has two quantum numbers. Just like in our electron, we're used to that with electron configurations and so on. We have the principal quantum number, N, which is 1, 2, 3. See the periods of the periodic table. So let's like pick the valence electron on sodium, okay? That last electron that goes into sodium has 4 quantum numbers. It's got a principal quantum number, N equals 3, because you see it's on row 3. Okay, it's in an s orbital, so L is equal to 0. And it has 3 options, or it has options that are bound by L. It could be minus L to plus L. Well, if L is 0, then the M sub L has to be 0. And then it can be spin up or spin down. So it would be plus a half or minus a half. So there's 4 quantum numbers associated with every electron in every atom. Okay. Well, here we have a molecule that's spinning and vibrating, and it has 2 quantum numbers to describe its rotation and vibrational thing. So don't be freaked out by something, an energy level having 2 quantum numbers, when we're already, as a freshman, learned that an electron's energy level can have 4 quantum numbers. Okay. So it has J equals 0, V equals 0, or it could have V equals 0, J equals 1, or V equals 0, J equals 2, or V equals 0, J equals 3, and this goes on and on and on. And at room temperature, we're going to have molecules that are spinning faster and faster and faster because of hot bands, because we have enough thermal energy to cause them to spin faster. So we might have molecules that are in J equals 50, but still at V equals 0. So we could have lots and lots of hot bands in the infrared and invisible. I mean, in the infrared spectrum. Okay, so that's the V equals 0. Now let's jump up to the V equals 1. So up here is V equals 1, and then we could have J equals 0, J equals 1, J equals 2, J equals 3. Is there anything uncertain about that? That seems straightforward, right? Okay, great. Now, that's the energy levels. The spectral lines are differences between the levels. I'm hammering that home in your head all semester. That the spectral lines, what we see in the spectrum, are differences in energy levels. And we have groups of selection rules. We can have J equals 0 if there's some sort of rotatory motion in the vibration. And then we can have delta J plus or minus 1. And then delta V is plus or minus 1. So we're going up, so they're all plus on the V's. The J's can be plus or minus 1. So let's do delta J equals 0 first. So notice this is Rovibrational, so we have to have a vibrational transition, and we have to have a rotational transition. So this is going from 0, 0 here to 1, 0, so 1 in the vibration and 0 up there. So you see how that's delta J equals 0. Everybody cool with that? Okay, and we'll just call that green. That's a green photon, even though it would be in the infrared, but I'm just sort of red arrows and yellow arrows would be shorter than the green arrow, and blue arrows and purple arrows and so on would be longer than the green. So I'm sort of using visible analogies here, but it's all in the infrared. Okay. What about the 1 to 1? So yeah, this is going from 0 to 1 in the vibration and 1 to 1 in the delta J. So it's still a delta J of 0. And it would be the same length. The only difference between those is that they're starting in different J values. And then what about the 2 to 2? Same length. So all of these are the same frequency or the same energy difference. And that's what we would call the Q branch line. So that's going to be right in the middle. And we saw that on the previous slide. If you look in your notes, the P, Q, and R branches and CO2, that Q branch was really tall because all of those transitions are on top of each other. Every one of those hot band jumps with a delta J of 0 is all at the same frequency. So you have that big peak in the middle. The Q branch is huge. Okay. So that's Q0, Q1, Q2, Q3 of what we've shown. Now let's look at the delta J plus 1. So look at the delta J. So it started at 0 here, and it went to 1. Okay, so I'll just put a 0 to 1. So that's delta J plus 1, and it's you know, a little more blue. Okay, I'm trying to just show. So it's a little bit longer arrow, and then the next one is even longer. It's going from 1 down here to 2 up here. And then the next one would go from 2 to 3. And since these are going up by J squared, these arrows are getting longer and longer and longer. So this one's going from 2 to 3. I could start one into 3, but I don't have a 4th level up there on my plot. There is one, but I'm just showing you the ones that I have the ability to plot. And so this in the spectrum would show up here at R0. So we would label that R0, label this one R1, and that one R2. So that's the R branch. The R branches are all the delta J plus ones. Okay. Now let's do the P branch. So delta J minus 1. I can't start at 0 because there are no negative quantum numbers in this situation. So I have to start at 1 and go down to 0. So even though the arrow's going up, I'm going down in J quantum number. See, this one's starting at level 1 and going to level 0. So delta J is shrinking. Even though I'm going up in vibrational quantum number, the molecule is slowing down in terms of its rotation. So its vibration is increasing, but it's rotating slower. And that's just because the angular momentum of the light hit this spinning molecule in the opposite direction and slowed it down 1. But it still excited the vibration. It's kind of weird, but that's what's going on. So molecule spinning, say this way, and vibrating. I come in with oscillating light that has an angular momentum going in opposite direction of that molecule, hits it, slows it down 1 unit, but still excites the vibration. How does all that happen? It's waves. Waves, you know, next time you're in a bathtub, swash your legs around and look at what the waves do. Waves are crazy. They can do all kinds of things, and that's what's going on with this. Okay. All right, so then this could go from 2 down to 1. So this is 2 to 1, and then we could have a 3 to 2. So this one's going from 3 down here to 2 up there. And we can't show any more because I don't have a 4th level on the lower side. So let's see where these would show up. These would show up, since that arrow, yellow arrow, is shorter than the green. When you convert it to wavelength, it's a longer wavelength or a smaller wave number value. And then the orange one is even smaller than that, and then the red one's even smaller than that. So we have this equal spacing of P1, P2, P3. So we have the P, Q, and R branches. As we go up in wave number, they're alphabetical in wave number. So if wave number is going up, that way we have the P, the Q, and the R. Okay. Wavelength is this way. So these are the longer wavelengths. These are the higher wave numbers. They're inversely related. And so this is how we label them, P, Q, and R. And this is it. So this is the P line. Let's say P3. Let's pick this one here. We would know that delta J is minus 1 because it's a P. Okay? And we know it started at J equals 3 because of the 3. So we will label these things like this. This is P3, and we know it started in level 3, and it went down by 1 in terms of the rotational quantum number. All of these go from 0 to 1 in vibrational quantum number. So we don't even have to really worry about the vibrational quantum number. It's the rotational quantum states that we're keeping track of. So that's the rho vibrational spectrum. This right here is the rho vibrational spectrum for a molecule explained. And that's what we saw in the previous slide on the CO2 bending motion. We saw the P, Q, and R branch. We saw the little wiggles. Those were the rotational lines. We saw the big Q branch. That was the one in the middle. Anything I can clear up for you? We'll do Raman in a minute. Okay. So this is the numbers. So we showed it sort of conceptually using arrows. So let's look at the numbers. So let's, the energy is the sum of the vibration and rotational energy equations. So you can see that we have this total energy here. It's the vibrational energy plus the rotational energy. This is the vibrational energy equation. Hc nu tilde, which means it's in wave numbers there. Hc converts it to joules if you wanted to use everything in joules. And then we have the V quantum number. So that's the quantum number plus a half. And then we have this, this actually should probably have a tilde on the B too. So the B is in wave numbers. So HCB tilde, J times J plus 1. So this is the rotational quantum number. So let's figure out what. Now there are some other terms, the anharmonicity for the vibrations, right? We could have those higher order terms. And we could also have centrifugal distortion. That sounds exactly like what it is. So if we got a molecule, let's say it's a diatomic, so these are the two atoms, and it's spinning faster and faster and faster, well, they're going to start pulling apart. And so the structure of the molecule is going to change the faster it spins. So at high J values, the bond length is stretched a little bit. If you stretch the bond length, you change the B value. And so we would need some correction terms to that at higher J values. So we'll see that in our carbon monoxide lab. So these are the combined selection rules. And let's look at the transition equations. So for the P branch, we take the V, notice it's V plus 1, J minus 1, and we subtract the E of V and J. So this is the result. I did not do the algebra for you, but you can verify with yourself after class that this is the result of that difference. Okay, so we take this, and wherever there's this V, we put in V plus 1, and then we subtract the one with V, and then here we put in J minus 1 in for J. And then we subtract this equation, and we do all the algebra, and this is what comes out for the P branches. Then for the Q branch, the J's don't change, and so they disappear. And we just have the change in vibrational frequency. And then for the R branch, we end up with this. Okay. So for our spectrum, this is what it looks like. From that Q branch, the 0 to 1, so if we put in 0 for the R, if we put 0 here, we end up with 0 plus 1, which is just 1, times 2b plus nu. So this is going to be 2b, twice the rotational constant distance from the Q branch. And then if we go up to J equals 1, so the 1 to 2 transition now would be another unit of 2b. And then the 2 to 3 would be another unit of 2b. So all of these are separated by two values of the rotational constant. And then the same for this one. If we go from 1 to 0, J starts out at 1. So we have the vibrational frequency minus 2b. And then if we subtract 2 of those, then it's going to go down 4 b's, but that means there's a difference between the 1 to 0 and 2 to 1 peak of 2b and here. So we're going to have spacing of twice the rotational constant between all the rotational peaks. Okay. So let's look at the rho vibrational Raman. So notice that I've got this scattering. So it comes up, the visible photon comes in, and out. And the difference between those is going to be the Rovibrational transition. But we have different selection rules. Now we have plus or minus 2 instead of plus or minus 1. So we still have the Q branches, okay? So those are going to show up in the spectrum, and then surrounding the Q branches we have not a P branch or an R branch. We have it's a plus or minus 2. So what is after R? S, right? So alphabetically we would have an S branch, and so this is from 0 to 2. See, this one goes from 0 down here to 2 there, so that's the plus 2 one. The next one starts at 1 and goes up to 3, and that's all I can show because I don't have enough energy levels there. But the trend would just continue. And so that's going to be the S0 line because it starts at 0 and goes up by 2. S tells you it's a plus 2. And then this is the S1 line because it starts at 1 and will go to 3 because S tells you it's a plus 2. And now let's do the O branch. So what's before P? O. So O, P, Q, R, S. Those are the different branches of lines. We never see them all in the same spectrum because the O and the S are in the Raman experiment. The P and the R are in the infrared experiment. The Q is in both. So this one is the 2 down to 0. So this one starts at 2 and goes down to 0. And the next one starts at 3 and goes down to 1. And we can't go, we can't start at 1 because it would have to go to minus 1. And we don't have any negative levels. So we have the O2 and the O3. So that's the O branch, Q branch, and S branch. So that's natural. I mean, you can imagine I'm going to be able to ask lots of questions about this, right? Which of these branches are in the infrared, you know, and if I put O and S in there, you know it's not in the infrared, so that's not the answer. Okay. So this is how we label it. Whenever you see O, you know delta J is minus 2. If you see S, delta J is plus 2. If you see Q, delta J is 0. And then the subscript is always the quantum state that it starts in. So it starts at 3 and goes down to 1. So those are the Raman Rovibrational spectrum. And so let's look at the transition equations in Raman shift. So Raman shift is that incident photon, the laser, and the scattered light that comes out. We take the difference and we get Raman shift. And so what we were showing here, these arrows are the difference between the laser and the scattered photon. So these arrows are Raman shift. Okay. So we're going to get the equation for the O, Q, and S branches. So we put in the selection rules for the O branch of delta J minus 2 and do the algebra, and this is what comes out. Okay. And our first value of J is 2 because it's going down to 0. So 2 minus a half is 3 halves, and 3 halves times 4, 4 times 3 is 12, divided by 2 is 6, so we have 6B. So we would subtract 6B from the vibrational center. The Q branch is delta J 0, so the J values all cancel out, and then the S branch is delta J plus 2, so it starts out at 0. Okay, so we have 3 halves times 4, again we'll have plus 6B. So our spectrum is 6B gap between the Q branch and the first R branch, and then from that point on we get a unit of 4B. So we have 4B spacing between all of our rotational lines. But we start out with that initial 6B gap on both sides, and then we have 4B after that. So we have this Hamlet here. He ponders to be or not to be. That is the question. Well, DW says if it's absorption, the answer is to be. Yes. But if it's Raman, it's 4B. And what we're talking about is the spacing between the rotational lines. This is important for the reason that if you're going to be doing this spacing between the lines and determining what B is, you've got to know whether you divide that spacing by 2 or divide that spacing by 4, because units won't help you there. So that's why I really emphasize this. Anytime where units won't guide you through the problem is sort of it's like a pothole on the road of solving a problem. Normally units are your problem, right? You got joules per mole here and you got wave numbers here. How to get from one to the other? You got to use Avogadro's number and the speed of light in centimeters per second and all of this crazy stuff using the units. Here, units won't help you. You have to know if I'm in the absorption spectrum, it's 2 times the B spacing. Spacing is 2 times the B, and if I'm in the Raman experiment, it's 4B. So this is your spectrum that you're going to analyze, the carbon monoxide spectrum. And every one of those rotational peaks is separated by twice the rotational constant. Why do I care? Well, the rotational constant has the bond length in the denominator, and it has the mass of the particles. We're going to look up the isotopic masses, so we have no uncertainty in the masses. I mean, it's out in the 7th or 8th significant figure. So carbon 12 is by definition 12, and oxygen 16 is really like 15.999 something or there. So we know those masses really well. What we don't know is the bond length. So we will find B and we'll solve for the bond length using a regression analysis. Diatomics can't have Q branches, and so that's why there's no Q branch. So on the low wave number side, here's transition energy, 2250 over here, 2050 over here. So that's the low wave number side. So in terms of wave number, this is the P branch. Then the missing Q branch, and then we have the R branch. So the R branch is always on the high wave number side, the P branch is always on the low wave number side, and a lot of times infrared spectra is plotted where the high wave number is on the left. And so here I've flipped it. Now the high wave number side is over here. So now the R branch is on this side. Wait, yeah, P branch over here, R branch is on this side because that's the high wave number side. So you can't say it's on the left or right. You have to say it's on the high wave number side is the R branch. So let's do some calculations. So I've got B. What do I do with it? Well, you see that R down in the denominator. That's going to be our bond length. This is the conversion. Like I said, it's all about the units, right? We want bond length in angstroms. Let me just use my pen here. Bond length in angstroms. And so, but we've got things that like Planck's constant up here that are in kilograms and meters squared. And so I got to get out of meters squared and into angstrom squared. So 1 angstrom is 10 to the minus 10 meters. And so if I'm doing squared, I've got to square that and make it 20. So there's 10 to the 20 angstrom squared for every meter squared. Okay, so that's one way to cancel that. And then I'm going to want just to use my isotopic masses in 12 and 15.99999 for oxygen and to calculate my reduced mass. But I would like to use grams per mole. I would not like to have to convert all of those to kilograms. And so we're going to need some grams to kilogram conversion. We've got Avogadro's number here. We've got the speed of light in centimeters per second. Notice none of these constants change in this problem. So do yourself a favor. Take all of those constants with all their sig figs and just multiply and divide them all and make your own constant. Consolidate this mess into one constant. And now you have an equation that you can use your reduced mass in grams per mole, and you can use your bond lengths in angstroms, but keep all of those significant figures. So that's note card bait. Okay, it makes things a lot faster. Notice there are not even any 10 to this. Okay, so you do it once, make sure you get it right, and then you don't have to worry about times 10 to the this and times 10 to the minus 34 and times 10 to the positive 23, and just make your life easier. Okay, but use all of the sig figs, especially for your lab, so that you don't introduce error. So keep all of these digits that you have here, and now you can solve for B if you have the bond length, or you could flop those around and put R squared over here and B down here, take the square root, and you get the bond length. Okay. So let's use B to solve for bond length. The S branch lines in the Raman spectrum are 3.56 wave numbers apart. What's the bond length of F2? Okay. For the masses, F2 is 38 grams per mole. Okay. So where do we get this mu? Let's calculate that first. Mu is equal to M1 times M2 over M1 plus M2. Do I do this one? Yeah, here it is for a homonuclear diatomic. Okay, so I have M squared on top because it's homonuclear, divided by 2M. And so then the M's cancel, we have M1 over 2. So that's real simple to calculate that. That's half the fluorine mass. We're swapping the bond length and the rotational constant. So the bond length is the square root of that whole mess over mu BE. But here's where units don't help you, right? We have to know that this is a Raman experiment. It's an S branch. And so we've got to take this number and divide by 4. To get B. So there's no units that are going to tell you to do that. You have to know that the Raman spacing is 4B. And that's why I did the whole Hamlet thing and made a big deal out of it. Okay. Put all the numbers in, do your calculation, and you get 1.41 angstroms. So that's it. So once we measure the rotational constant, we can calculate the bond length. Now, which one do I use? I've got all those peaks, and every one of those peak differences gives me a different B. Do I take the average? How many times do I do this? That's a real tedious calculation. If I've got 50 differences, then I've got 50 calculations of B and 50 bond lengths. And that doesn't sound right. So we do a linear regression. We do a trend line, and we get that. So this is how you would do this on your carbon monoxide lab. You have your carbon monoxide spectrum, and you have the P and R branches, and then we're going to assign those. We're going to assign quantum states to them. So this is P1. The one closest to the middle is the 1 to 0 P line. Starts in 1 down here at V equals 0 and goes to 0 up here at V equals 1. That's delta J minus 1. So that's P1. The next one, and then the other one, the first one is R0. It starts at 0 and goes plus 1. So that's R0 to 1. And then the next one on the P branch side is P2, P3, P4. You see the trend all the way down. So we have easily 25, and there may be another few. Okay, so go as far as you can go until the peaks start getting into the noise. Okay, and this is where you can use your scientific judgment. Okay, we're going to let you do some decisions here. When you get out here and it gets close to the noise, how do you know if it's noise or a peak? And so look at the differences between those. You may have just on the side in your Excel sheet, do like P25 and P26, and then take the difference between those frequencies, and you see a trend, and then 26 to 27, you see a trend. And then if you pick noise, it's probably not going to follow the trend. So you've got a difference, a difference, a difference, and then the differences get worse. Now you're picking noise. Okay, so you don't want to pick noise. So you go back and get rid of the noise ones. The more peaks that you get, the better your centrifugal distortion constant will be. And you really want to see how that bond stretches with spinning. So, then we do the same thing with the R branch, R1, R2, R3. Does everybody see the trend all the way down? Here we have a different problem. We're not just going down to the noise, we start running into another spectrum. So this is carbon monoxide, and we start to run into the carbon dioxide spectrum. So you don't want to pick carbon dioxide peaks. You want to pick as many carbon monoxide peaks. Notice the intensity is going down. If you start picking peaks that are going up, you're on the wrong spectrum. Okay, so your intensity has to go down, and then you could use the same kind of thing about noise. If the differences start getting random, then you're picking noise and you're not picking your peaks. You might be able to get to 26. Maybe that's 27. I don't know. You decide. And maybe 28. So it's 6 26, 27. You can decide whether you think those are valid or not. And so you get to do that. Okay. Still, that's just shown here. That's 24 measurements of B. Here's another 24 measurements of B because of the differences. And so we have 50 measurements of B. So we could calculate the bond length 50 different times. We don't want to do that by hand. Okay. So what we want to do is, and plus, which do we use? Do we use the P branch to calculate our average B? Do we use the R branch to calculate our average B? We can make a fake quantum number that that can be assigned to every one of those peaks. And that's what we have up here. See on there, on the R branch, it says M equals J plus 1. And so for R0, M is equal to 1. And for R1, M is equal to 2. So we could just label these with this running fake quantum number, M. So the R branch, they're positive, and on the P branch, they're negative. For the P branch, M is equal to minus J. So for P1, M is minus 1. For P2, M is minus 2. And now we have a single quantum number that's really not a real quantum number, but it's good for our regression analysis. We have an M quantum number that we can do the regression on. And where it crosses 0 at the intercept, then that's going to be the vibrational frequency. So let's look at this regression analysis. There's going to be a handout that's copied from the literature from my former advisor, Joe Nibbler at Oregon State, where I went and got my PhD. He wrote a PChem experiment book, and this is his lab. He has this equation up here. Yes? Yes. No, this is just for the regression analysis. So it's sort of like a trick that we're using. Yeah, and so for the P branch, they're all negative, and for the R branch, they're all positive. And then when we do the regression, there'll be an intercept where there's 0, and that's right where the vibrational frequency is. Yeah. And so Joe Nibbler, he has this equation, the transition equation related to the J quantum numbers, okay, for the P branch and the R branch and so on, but we could combine them using this M quantum number. So this is the equation he has in his book. But I've modified it a little further. So just like all good students, you take what your teacher taught you and you extend it, okay? So he taught me this lab, now I've made it even better. And so we could do this regression with respect to M squared, M cubed. Do you remember the Excel boot camp? You had that polynomial, and you had the trend line, and so you had the value in front of x squared, x, and then the intercept. That's what we're going to be doing with this, and we could do this instead of x with respect to M. But when we solve for the coefficients of those, the coefficient in front of the M cubed term would be minus 4dE, and the coefficient in front of the M squared term would be minus alpha E. That's that rotation vibration coupling constant. And then the slope, or the coefficient in front of M, would be this complicated thing. And that's not very nice or elegant, okay? What I want to come out of my regression analysis are these constants by themselves. So I did some algebra, and this is the equation you want to use, okay? Use my equation, not Nibbler's. So our columns are going to be, column 1 is going to be 2 times M. So there'll be a column that's 2M, and then there'll be a column that is minus 2M minus M squared. So once you assign your quantum numbers, then you just make these columns, okay? And then column 3 will be minus M cubed. And when you do a regression on that, you get these coefficients here, here, and here. And then the intercept is nu 0. So this output, this regression output, is going to have our nu 0, our BE, our alpha E, and our centrifugal distortion constant. And we're not going to have to do any algebra to get to those. They're going to come right out of the regression. And they're going to have their standard errors listed right here. So we know this vibrational frequency really well now. It's 2885.8869. So I would round it right here at 69, keeping 2 digits of uncertainty. So you see the standard error is telling you where you're uncertain. We don't have to use the significant figure convention, accounting sig figs, when we're doing like a regression analysis or something. It's telling us where our uncertainty is. The significant figure convention says save all your certain digits and one uncertain digit. And you have to guess where you're uncertain. Like if I give you 4.56, I'm telling you I've got 4.56. I'm telling you I'm certain about 4.5, and the 6 is uncertain. So I'm going to keep that digit of uncertainty. But here, that's only if you have this first column of numbers. When you get the standard error column of numbers, now you know where you're uncertain. And I see a lot of times in literature they keep two figures of uncertainty. So 0.00054, that's where our uncertainty is. And so we would round our number the same place. So we would round this BE right there, 10.59025. So if I was reporting this with the value plus or minus my standard error, then that would be my standard error. Look at this one. This is 7.5 times 10 to the minus 5. So I would just keep 2 of those. And so that's going to be all the way out here. 1, 2, 3, 4, 5. So we would round that right there and put like the 7.4 next to it. And then this is the uncertainty in my centrifugal distortion constant. So 1, 2, 3, 4, 5, 6. So 4, 5, 6. So I would keep those. So you could write this out, 0.0005186, and you could put 3, 1 in parentheses. So the way you write that 3, 1, that's that the place value for that 3, 1 is where that 86 is, and we can talk some more about that later. Then we use those standard error columns to produce the 95% confidence intervals. And we've got our vibrational frequency, we've got our rotational constant, our alpha, which is the vibration rotation coupling constant, where as it vibrates, it can rotate faster and slower as it goes around. We have the centrifugal distortion. We're going to have to take BE and calculate R. So that's why there's that lecture on Blackboard on propagation of uncertainty. How do we get the uncertainty in R if we know the uncertainty in B? And the same thing for K. We use the vibrational frequency to get the force constant. So we got to propagate uncertainty there too. So this is a sort of quick rundown on the lab you're going to do. So you're going to do Rovibrational spectroscopy. You're going to assign the quantum numbers to all the J values, and you're going to solve for the bond length of carbon monoxide and get all these other physical constants too. So it's pretty cool. So this is essentially what you're going to do. So when you get your B values, you're going to use that to calculate the uncertainty in R, and then you're going to use your vibrational frequency to calculate K. Use the most accurate masses. So use all of the decimal places for your masses. Okay. And you can compare that force constant to carbon monoxide and I2 from the Gaussian labs. You calculated those force constants. Now is when you pull those out and say, and from my Gaussian calculations, we have this force constant for this and this bond length for this. And so have fun. You're combining the labs that you've already done. And then there's some extra calculations in the notes. We don't really have to go through these, but they're there for your edification. So this is just showing you that the Raman shift values these are the visible photons. This is why this goes through glass. You know, we can do Raman through glass because these are visible photons and they're not absorbed by glass. But we're looking at transitions that would be in the infrared if we did them directly. Okay, I think that's all I've got for you.